Hello, this video includes information on potential free energy and equilibrium, as well as batteries and fuel cells.
Let's connect this to equilibrium, which is what we talked about in the last couple of chapters. So when we look at galvanic cells, they take chemical energy in that redox reaction and they convert it to electrical energy. And the electrical energy can do work. So that gives us an equation. Okay, the electrical work that can be done by a galvanic cell equals the potential difference between the reduction and the oxidation times the charge, and the charge is in terms of coulombs. Now, the charge of one electron equals 1.602 times 10 to the minus 19 coulombs. This is a constant. And if we wanted the charge for a mole of electrons, because we usually don't talk about things in terms of one electron, it's usually a mole of electrons. We can convert a mole of electrons to electrons, knowing that Avogadro's number of electrons equals 1 mole. And then we can convert electrons to charge. So 1 mole of electrons is equal to 9.65 times 10 to the 4 coulombs per mole of electrons. And this constant has a name. Okay, it's called Faraday's constant. 9.65 times 10 to the 4 coulombs. So we're going to look at an equation here that relates work to our reduction potential. The W in that equation stands for the electrical work. N stands for the number of moles of electrons in that system. F stands for Faraday's constant in terms of coulombs per mole of electrons. And our E cell is our cell potential. The negative sign here is there because the system, the galvanic cell, is doing work on the surroundings. Now, to relate that to our free energy value or our G value, okay, the free energy is the energy that's available to do work. So what we can essentially do is substitute in delta G for W. So this is the equation that we would work with to relate free energy to our potential difference. If delta G is less than 1, if delta G is a negative value, we know that that means it's a spontaneous process. We learned that in a previous chapter. And if delta E for our cell, if our reduction potential value for our cell is positive, we know that the process is going to be a spontaneous process. Delta G equals negative NFE. This is a new equation. Delta G also equals negative RT ln of K. This is an old equation that relates free energy to equilibrium. We can set these two equations equal to each other. Since we've got delta G here and we've got delta G here, this value equals this value. If we want to calculate just the potential difference, we would just divide both sides by negative NF, and that gives us a new equation. And this new equation has lots of constants in it. Okay, we've got R, which is a constant. We've got T, which is, if we're at standard conditions, is 25 degrees Celsius or 298 Kelvin. And we've got Faraday's constant, which is a constant. So 8.314 times 298.15 divided by 9.65 times 10 to the fourth can be summarized in a constant, 0.0257 volts. It's just taking the three constants and putting them together in one constant. We can summarize this by saying that the voltage across a cell equals 0.0257 divided by N, that's the number of moles of electrons, times ln of K. We can also convert that. Instead of using ln, we could use our log, and we've got 0.0592 divided by N times the log of K. So whether we want to use the ln value or we want to use the log value will give us a little bit of a different equation. So this relates everything here. We've got delta G, that's our free energy, and we've got K, that's our equilibrium constant. And we already looked at this equation here. So delta G equals negative RT ln of K. Now we're just going to add in this new variable, our potential difference. Okay, so if we want to relate our free energy to E, we've got negative NF times E equals delta G. And if we want to relate E to K, E equals RT over NF times the ln of K. A reaction is spontaneous if K is bigger than 1, so we have more product than reactant. Our free energy is a negative value, delta G is a negative value, and our potential difference is a positive value. A reaction is non-spontaneous if K is less than 1, so reactants are bigger than products. Delta G is a positive value, or our voltage is a negative value. And the reaction's at equilibrium if K equals 1, delta G equals 0, and E equals 0. So let's look at a problem. Okay, we're given tin atoms reacting with copper ions to form tin ions and copper atoms. We look up on the table the value for the oxidation, negative 0.134 or 138, the value for the reduction, 0.153. So step number 1, calculate the potential difference between the reduction and the oxidation. So you're taking the cathode value and subtracting the anode value and see what you get for the voltage across our cell. The cathode is 0.153. The anode is 0.138. So 0.153 minus negative 0.138 gives us positive 0.291. Next thing we want to calculate, what's the free energy? We're going to take negative N times F times E for our cell. The N is the number of electrons. So in this case, 2 electrons are being lost in our oxidation, 2 electrons are being gained in our reduction, so N equals 2. F is Faraday's constant. E, we just calculated here, 0.291. So we've got negative 2 times 9.65 times 10 to the 4th coulombs per mole of electrons times 0.291. Again, We calculated the 0.291 here. This value is Faraday's constant, so it's always going to be this number. And the 2 is the moles of electrons that are being transferred between our oxidation and our reduction. So delta G is 56,200 joules per mole of electrons, or negative there should be a negative sign here, negative 56.2 kilojoules per mole. Now that we know delta G and we know E, we can calculate K. We're going to multiply both sides by 0.0257 and divide both sides by 0.0257, multiply both sides by N, and that'll leave us with ln of K. So the ln of K equals E times N over 0.0257. Now, we don't want the ln of K, we just want K. And if you look on your calculator and you find the ln button, the second function of that is the e to the x button. So K equals E to the E times N divided by 0.0257. So K equals 6.83 times 10 to the 9. All right, so to look at the numbers, E is 0.291. Delta G is negative 56.2, and K is 6.83 times 10 to the 9th. Okay, that means E is greater than 0. Delta G is less than 0. And K is bigger than 1. That means this reaction is spontaneous under standard conditions. Again, standard conditions being 1 molar concentrations, 25 degrees Celsius, and if we were talking about gases, 1 ATM for gases. There are no gases in this one. So what if we're not at standard conditions? Because often things are not at standard conditions. Well, now we have a little bit of a different equation, which we looked at in a couple of chapters ago. So if we were to look at our free energy at non-standard conditions, it equals our free energy at standard conditions. That's what this little 0 stands for. Plus RT ln of Q, that means we're not at equilibrium. We can substitute in for delta G, negative NFE, not at standard conditions. We can substitute in for delta G naught, negative NFE at standard conditions, plus RT ln of Q. So we're going to do a little manipulating with this equation. We're going to divide everything by negative NF. That cancels negative NF out on the left-hand side. It cancels negative NF here, and we're just left with E naught. And we're going to be dividing this by negative NF. So we get negative RT divided by NF ln of Q. And again, R is a constant, T is a constant, F is a constant. So we can just put all those constants together and come up with a new constant. And this equation is called our Nernst equation. So the voltage in a non-standard cell would equal the voltage in the standard cell minus 0.0257 divided by N times ln of Q, or just a slightly different version would be 0.0592 divided by N times the log of Q. There's just a different function. This is a log function. This is an ln function. It doesn't matter which one you use. And this is called the Nernst equation. So let's look at an example. This is a non-standard cell. How do we know that? Well, standard cells are 1 molar. This is only 0.15. And this is only 0.0025. So this is a non-standard cell. The aluminum is going from atoms to ions. So it's being oxidized. That would take place at the anode. We can look up the value on the table for aluminum, and it's negative 1.662. This comes off the reduction potential table. The copper ions are being reduced. Reduction takes place at the cathode compartment. And when we look that up on our reduction potential table, it's 0.34. So if we take the cathode value and subtract the anode value, 0.34 minus negative 1.662 gives us 2.00. Okay, that's the voltage across our cell. For Q, we would take our products over our reactants. So 0.15 squared over 0.025 cubed gives us 1,440 for our Q value. Now we can calculate the voltage across this non-standard cell. We would plug in the voltage if the cell was at standard conditions, which is 2.00. We would substitute in 6 for N because 6 electrons are being lost and 6 electrons are being gained in this equation. And we'd substitute in 1,440 for Q. And when we plug that in, the voltage across our cell is now 1.98. Okay, so let's look at that for a second. If the concentration of aluminum ions was 1 and the concentration of copper ions was 1, this would be a standard cell. And if this were a standard cell, the voltage across that cell would be 2.00 volts. But we're not at standard conditions. The molarities are not 1 molar. So the voltage across this cell would be less than what it was under standard conditions. That's what we mean when we talk about our Nernst equation. Batteries, we're going to go through this super quick. When we talk about batteries, batteries are electrochemical cells. Okay, they take chemical energy and convert it to electrical energy. They're essentially a galvanic cell. There are 2 types of batteries. There are primary batteries. Okay, those are ones that are one and done. You can't recharge a primary battery. A secondary battery is a battery that can be recharged. You use up the energy that was in that cell, and then you recharge it again. And that's as far as we're going to go for batteries. We're not going to go into any more detail on that.